You know, for over a century, physics has been built on a handful of fundamental constants. These are numbers we can measure with incredible precision, but we can't really explain where they come from. It's kind of been a roadblock in the hunt for a true theory of everything. So today, we're going to dive into a really radical idea. What if one of the most important constants in the universe isn't a fundamental rule at all, but just a side effect of its own structure? Just think about that for a second. Imagine if the number that underpins the entire quantum world, a number we've always just accepted as a given, was actually just a consequence of the universe's shape and its rhythm. That's the wild idea we're going to unpack right now.
Okay, so to really get why this is such a huge deal, we first need to understand the mystery that sits right at the very heart of quantum mechanics. And it all boils down to one single, incredibly important number.
So here it is, Planck's constant. You'll often see it written as h bar or h bar. A fantastic way to think about it is like the pixel size of the universe. It sets the resolution of reality itself, the smallest possible jump that energy can make. Pretty much every quantum calculation you can think of depends on this number.
Now that word axiomatic is everything here. In physics, that basically means we accept it as a self-evident truth, no questions asked. We plug it into our equations, and hey, it works. But we have no deeper theory for why it has the very specific value it does. It's like a foundational rule in the rulebook of the universe with no known author.
So, how in the world could we possibly explain where a number like that comes from? Well, a new perspective, called the Harmonic Scale Framework, thinks it has an answer. And it does it by completely reframing how we look at, well, everything. The Harmonic Scale Framework, or HSF for short, suggests that maybe we've been looking at this problem completely backward. Instead of starting with these mysterious constants, it starts with a simple, kind of beautiful idea about the very fabric of reality.
So in the HSF view, you have to kind of rewire your brain a little. The universe isn't a collection of separate little things. It's one single vibrating entity. Particles, like an electron, they aren't tiny little balls. They're more like stable musical notes, what physicists call standing resonances. And here's the key. All of this is happening on a shared cosmic boundary, almost like vibrations on the surface of a drum, with a sort of master clock wave setting the tempo for the whole show.
So, starting from that big picture, HSF builds its entire logic on just 5 core principles. It's how these 5 simple rules work together that leads to its most mind-blowing conclusion. Let's walk through them one by one.
All right, let's break these down. First up, the binary ladder. Frequencies in this universe aren't just random, they scale in a simple doubling pattern, just like musical octaves. Second, the spheroid. All this stuff is happening inside a shared container, a slightly flattened sphere. Third, the timing anchor. A very, very slow cosmological wave acts as a master clock, giving us a base frequency. Fourth, and this one is absolutely crucial, equal energy. Every single possible note or mode holds the exact same little packet of energy. And finally, finite modes. Any object we see, like an electron, is just a collection of a specific, finite number of these little notes.
Okay, so we have our 5 rules. Now for the magic trick. With those rules in place, HSF claims it can now build Planck's constant from the ground up without ever having to assume it exists in the first place. Let's see how they pull it off.
It all kicks off with a pretty simple idea, actually. HSF defines Planck's constant as the energy of one of those fundamental notes we just talked about divided by the universe's base clock rate, or its fundamental frequency. Seems pretty straightforward so far, right? Okay, next up, we need to figure out the energy of just one of those modes. Well, remember Rule 4? All modes have the exact same energy. So if we take the total energy of a particle we know and love, like an electron, which we know from its mass, thanks to E = mc squared, and we just divide it by the total number of modes that make up that electron, boom, we get the energy per mode. And what about that frequency on the bottom of the fraction? Where does that come from? Well, that comes directly from the universe's geometry, the size and shape of that flattened sphere we mentioned, and the speed of that master timing wave running across it. The structure itself is what dictates the timing. And here it is. This is the final, brilliant step. When you plug all those pieces into that first simple equation, you get this expression for Planck's constant. But look closely. There are no unexplained axiomatic numbers here. Every single thing in that equation, the electron's mass, the number of modes, the radius and shape of the universe, it's all a physical, measurable property of the cosmos. So, why does any of this matter? I mean, this is a huge deal. If HSF is correct, it means physics could have an entirely new foundation. It's a massive shift from just accepting a rule to actually deriving that rule from the shape of the universe itself.
This slide really puts it all in perspective. We go from the conventional view, where Planck's constant is this rule that's just etched in stone and we have to accept it, to the HSF view, where it's what's called an emergent property. It's not a command the universe follows, it's a natural consequence of how the universe is built.
And the implications here are just profound. It would mean the constant isn't arbitrary at all. Its value is literally locked in by the geometry of the cosmos. It should be the same for every single particle, and most importantly for science, it's testable. The framework makes a concrete prediction. If your numbers for the universe's shape or the mode count are wrong, you'll calculate the wrong value for Planck's constant. This isn't just philosophy, it's a real theory you can actually test.
And that leaves us with this one, fascinating final question. We've always searched for the fundamental laws of physics as if they were these abstract, mathematical rules that were somehow imposed on reality from the outside. But what if the deepest rules aren't written down at all? What if they are simply the shape, the rhythm, and the harmony of the universe itself?